second day of the workshop on computational and statistical trade-offs in inference problems and rigorous evidence of thereof. And today we are starting with two talks that are coming here from EPFL, streamed to the whole world, and we are very happy to do that. And first of them is Florent Krzakala, that will tell us to be hard or not to be, the spike matrix tensor model. So we'll give him the stage. And also, yeah, I forgot to say before that the organizers, that majority of the organizers is actually sitting in the room on our side. There is also Afonso. Afonso, do you want to say hi?
I think just to prove that hi. I think I'm on the other camera.
Okay, cool.
People here just if you want to ask a question.
Okay, I'm sort of waiting for an official notification that I can start.
But you should start, please do.
Okay. All right. Okay, so I'm a little bit nervous, actually. I never did two seminars at the same time, so that's certainly interesting, but it's a welcome change after all these Zoom meetings. So it's good to be in person with everyone in Lausanne and in Berkeley, sort of. To make it feel more real, I made some, homemade Simon's cup. Now I really feel like I'm in the building. Okay, so let's start. And I will discuss, a trade-off between optimality and statistical optimality and algorithm. So I'll try to look at the camera from time to time, but sorry guys, we have a real audience here, so let's see how it goes. Okay, let's start with generic questions, which probably are of interest to everyone in this workshop, which are the following. So take a high-dimensional non-convex problem. You have to learn something. So there are many things you might want to do. If you are a Bayesian guy and if you have access to the posterior, you might want to do sampling because this is optimal MMSE estimator. So how hard is it? If you are more an optimization person, you might say, no, I want to do maximum likelihood. So you might ask, okay, how hard is it to compute maximum likelihood in general? And the sort of questions that we ask often are, okay, how does the energy or loss landscape is influencing that kind of questions? Okay, so these are very generic questions. And in particular, one of the visions we always have is that you have spurious minima in the landscape, and these spurious minima are evil and trying to annoy us. And since we are in this workshop, you might also wonder how these approaches compare with message passings, which for synthetic problems is an extremely good algorithm. Okay, so this is a bit what will be discussed here. And in context, I will try to discuss this in a very completely idealized model, a synthetic model which has absolutely no interest except that we can study it. And this is interest enough for me. And what I wanted to find, what we wanted to find with my collaborators was a problem where, you can compute analytically what are the optimal performances, information theoretically speaking, and you can analyze as precisely as we want or we could many algorithms, the behavior of many algorithms, so message passing, sampling, gradient descent, and so on and so forth. It turns out there is a model for which we can do this, which is the matrix tensor spike model on the sphere. Okay, so what is it? Okay, so let me define the model. It will not come as a surprise to many of you, because if you are in this crowd, you might have heard of the spike matrix model. So here it is. So first, take a norm vector on the sphere in n dimensions. So L2 norm is n. Let's call it x star. And this is what we want to find. Now, I'm not giving you x star. Instead, I'm creating a rank 1 matrix, which is x star transpose plus some Gaussian noise with variance delta. Okay, and I will rescale this part by square root of n to make it small, to make it hard. Now, I'm also creating a tensor, not only a matrix, I'm also creating a tensor, a rank P tensor. It's essentially the same kind of object, you know, it's rank P tensor made by a tensor product of the vector, plus again, some Gaussian noise. And notice here, a weird factorization, you know, a weird prefactor, which is just here so that in the large dimensional limit, we have a finite log likelihood ratio. But if you don't want it, you know, don't take it. You just change the scaling of the noise. All right, so now I'm giving you the tensor and the matrix, both of them, and your task is to find back X star. Right? Very well defined problem. And so this is how we would write it if we don't want any indices. And so the important parameter are delta 2 and delta p. I will basically take p equals 3, so delta 2 and delta 3, which are the noise for the matrix, and the noise added to the tensor. Okay? Or the variance of the noise. Okay. Now, if you're a physicist, you should be extremely happy right now because at least if you're on spin glass theory, you should recognize that this is nothing but your favorite model. It's called the p-spin glass model. In particular, if you define a cost function or an Hamiltonian in this way, well, the margin, you know, the Gibbs measure according to this Hamiltonian, which is written here, is just the posterior function. Okay, so physicists, when they see this, they say, oh, okay, I know that. This is just a p-spin. If you're not a physicist, forget it. And if you are, I'm sure you welcome this connection. That's literally the 2 plus p-spin model, except that the couplings have a rank 1 perturbation. Okay, and so either you want to sample from this measure, or you want to do maximum likelihood, which is finding the minimum of Hamilton. Okay, so what do we know? What do we know about this model? We know quite a lot, including some rigorous results, actually. So as you know, if you want to study information-theoretic performances, what you should what you should compute is the limit of the logarithm of the partition function. From this, you can compute everything. And you know, if you are from information theory, you will say, oh, well, from this, I can compute the mutual information. If you're a statistician, you will say, no, what I want is a likelihood ratio. Or you may want to compute the Kullback-Leibler divergence between the spike model and the null model. They are all given by this quantity. So essentially, computing this, the large n limit is what you want to do. Now, this can be done. And more importantly, this can be proven. We're quite good at proving these replica results now. And for this problem, informally, this is what we know. This quantity concentrates around the max of this function. So it's a very simple function, it's a function of one parameter. You can see here that we have this intensity of noises. And perhaps more importantly, once you compute the max of this function, and it's R max, M star, that maximizes this quantity, well, the best mean square error, the minimal mean square error is just 1 minus M star. Okay? You can maximize it explicitly, extremely easy, and this is what you got. So you even have the value of M star. So I don't know about you. For me, it's not entirely clear what M star is from looking at this. You can just plot it. This is M star as a function of delta 2 and delta 3. And you see that M star, there is a region where it's equal to 1. So 1 minus 1 is 0. It means in this region, the mean square error. Oh, that's the MMSE. Sorry, that's not M star. That's MMSE. So in this region, the MMSE is 1. And this is what a random estimator will do. So it's terrible. So you have a region here where you cannot learn anything. But even the optimal algorithm will just not give you anything better than random guess. And there are all these regions when you can do something.
Florent, what
yes.
is the other axis? M is a function of what?
Yeah, this is MMSE as a function of, okay, so on this side you have, you know what? Let's go on the next slide. But what you have is essentially the intensity of the noise for the tensor and the intensity of the noise for the matrix.
Okay.
Okay. Now let's forget the value of M star. Let's just ask, okay, is M star 0 or is it greater than 0? And we have a 2D plot, which is probably simpler to parse. Okay, so that's the important diagram. So here I have the signal to noise ratio, which is the inverse of the noise on the matrix. And since I'm really crazy and stupid, on this side, I'm plotting the inverse of the signal to noise ratio for tensor, which is the noise on the tensor. So it's a bit stupid. Maybe we should use the same convention for both, but we didn't. And now we are stuck with this notation. But essentially what we have here is the following. There is this region here, the red region, which is the region where the noise is large on the matrix and large on the tensor, where there is nothing we can do. And as far as, there is no learning possible, and the M star is actually 0. Okay? And then you have the blue region here, where M star is positive. So at least we can learn, we can get a noisy reconstruction of the signal. Okay? All right, so but basically everything there is to say about information-theoretic performances are here. Now, what are the best algorithms that we know for this problem? And for this synthetic problem, you will not be surprised that this is AMP, it's approximation message passing. So it was written, I think, for the first time for this tensor problem by Andrea and Richard. And it's straightforward to adapt it to the spike matrix and tensor. And this is how it looks. If you are familiar with it, you will recognize that this is essentially an iterative algorithm with these terms which are called Onsager terms. And the nice thing about AMP is that we can precisely characterize its performances through this tools called state evolution. And this is what AMP gives you. So AMP is actually, in this region here, able to find optimal performances. AMP finds M star. Below this line here, AMP is not giving you any better than a random guess. So there is this nice, interesting region here, where we know that there is a statistical to computational gap, which is the subject of this workshop. And so, okay, there is one of them. As far as we know, that's the best thing that can be done so far. And of course, we are waiting for someone to beat this threshold. Now, just a quick comment. There are two interesting limits that you might consider. One of them is if you are really, really adding a lot of noise to the tensor. And of course, if you have infinite noise in the tensor, or zero signal to noise ratio, well, there is no information in the tensor. What you should do is just look at the matrix. And then you are not surprised to see that this line is just the BDP transition. Okay, when you cross vertically here, the transition at 1 is just the one where if you look at the spectrum of the perturbed matrix, you have one eigenvalue that goes out of the dot. It's literally Benarous-Beck-Péchet transition. There is another limit which is interesting, which is, if you zoom in here, where you have basically infinite noise on the matrix, so you have only the tensor, and the tensor has extremely small noise. If you want, to do interesting thing, you should really look at this almost non-noisy tensor. And here we have algorithm which can enter the hard phase. For instance, this kind of tensor unfolding algorithm and so on and so forth. And we have spectral method devised by Alex, Ahmed, and Chris, and so on and so forth. So this is all interesting. I will not be discussing all this, okay? We just look at that. Delta is finite. Okay, I'm not looking to these extreme cases. Okay, this is all nice and everything, but the question I really want to ask now is not about AMP, it's about what about what people actually do. And what people do, if you are in a Bayesian department, they would just try to sample from the posterior using maybe Langevin, maybe MCMC. And if you go to speak to anyone doing machine learning, they will say, just put this in PyTorch and compute the gradient and do a brutal gradient descent. So how do these things perform? And that's what I really want to discuss here, and also how are they connected with the absence or presence of meaning. All right. So this can be answered in this model, which is the only reason why we did it. So let's do it. let me tell you what happened if you sample with the Langevin dynamics. Okay, I don't know about what happened if you do exactly MCMC, but with Langevin, we have a pretty good idea. Just remind to what Langevin is. Langevin is essentially an algorithm, stochastic algorithm, in which at each time, well, you're trying to do a gradient descent somehow, and you inject some noise to make sure that you can stay at a finite temperature. Okay. Now you may ask, what happens if you just run this at long time? And we can analyze that. It's one of the favorite tools of mathematicians, and it's extremely popular among physicists. The way we did it was by using this thing called path integrals, because we are physicists, we like fancy things. This is how it looks, but never mind that. The whole point is that you can really work hard and derive differential equation that tells you what is going on here. And we didn't do it, actually. People did it before us for the p-spin, because it's a favorite model of spinless people. That was done by Culiandolo and Kurchan, as well as Crisanti, Horner, and Summers. And for the problem without a spike, we even have a rigorous proof that these equations are correct. Okay, that was one of the beautiful achievements of Gérard, Amir, and Alice some years ago. So lo and behold, this is what we know. The Langevin the Langevin is perfectly described at this set of integral differential equations, which looks a bit annoying. But if you solve them, this part here, we tell you how you overlap with the hidden assignment will evolve with time if you start from 0, of course. Okay, so you just have to solve this, which it's not easy, but you can plug it in a computer. And if you do this, you can plug it in a computer and see what happens. So this is what happens. The first thing you should realize is that if I iterate IMP, after 20 or 30 iterations, IMP is finding a positive magnetization or positive overlap. It's pretty fast. Langevin is doing the same, but if you see my time scale here, see that it's 10 to the 5, 10 to the 4, so much slower. And well, slower. So you might say, fine, Langevin is slower, but it's a good tool. So maybe if we really, it's just maybe a prefactor, and if you let it run long time, we find the correct value, or at least it's maybe as good as IMP. So we try to test this assumption, and unfortunately, it looks that this might not be the case. So for instance, here, this is delta P. This is magnetization reached by IMP after like 100 or 200 steps. Okay, it's positive. Now, this curve is what is reached by Langevin after 1,000 steps. So here it's perfect. It actually finds M star, which it must, of course, because it's an algorithm which is sampling from the posterior. So at some point, if it's sampling correctly, must return you an overlap which is base optimal. Okay, run it longer, and you see that if you run it longer, at some point it starts to be good here, but then you run out of computer time, and not clear that that this is going really all the way to 0. So if you want to answer that, you have no choice. You look at the equation, you work really, really hard. We try to do this, and we estimated analytically. It's not rigorous, by the way, but we did our best to estimate when it starts to work. And we have a line here. This is the formula. And Langevin works here. In this whole region here, Langevin does not work in linear time. So it's Langevin hard, if you will. So that was interesting for us. I was not expecting this. I was completely expecting that Langevin will do the exact same thing as message passing. I would have told you, of course, only a fool will believe that this is not true, but that's what we found.
Does Langevin work in, Florent, does Langevin work in polynomial time here, just not linear time? Like, or do you have no way to predict this?
All linear time.
This is all for linear. Yeah, but okay, theoretically, what should happen if I run it for n cubed time? Like, should it catch up to AMP?
I don't know. And maybe, I will not make a guess now because apparently my intuition is bad. Okay, let me make a guess. I think it will need exponential time, but.
Okay, so it should really be bad. Okay, thanks.
Yeah. I really don't know. Okay, now I have one slide to give you the intuition that we have on it right now, which is kind of for replica geeks. So if you're not, sorry, but this is essentially an understanding that was made. I was not on the paper, actually. It's Lenka who told me this, with Silvio Franz, Pier Francesco Urbani, and Antenucci. So here is what is going on. If you think about the free energy condition at a given value of the overlap, okay, which is nothing else than the usual quantity, but you have an indicator function. You can plot it. It's like this, and the max is m star. Okay. Now, IMP is trying to optimize what we call the replica symmetric potential. We know that at the maximum here, the replica symmetric potential is correct in the sense that it gives you the correct value here at m star. Note that when IMP works, the potential is sort of, not exactly convex. IMP starts from here and is going there. Now, the thing which is interesting is that if you compare the replica symmetric potential, the actual potential, the actual free energy condition at the value of m, it's not given by the replica symmetric approximation, it's given by RSB. There is replica symmetry breaking. Not at the maximum, mind you, because we proved that the maximum was correct. But for values of m which are not m star, they differ, and you have that kind of non-convexity, and somehow, I feel that Langevin is trapped here. And I don't know how much of an explanation it is, but I think it's interesting. Somehow, the paradox is that IMP is optimizing the wrong potential, and since it doesn't know it's impossible, it's doing it. It's doing it, and I found it a bit magical. And so I think this is interesting and certainly surprising for me. Okay, part three, sorry. What about gradient descent? Okay, so since we know to do Langevin, we know to do gradient descent. We just have to take, well, we don't know to do gradient descent, but we know to do gradient flow. It's just Langevin when the noise is, when the temperature is going to 0, and then this is really like following gradient flow. So we looked at gradient flow. We have the same kind of equation. We can work really hard, blah, blah, blah. And what is going on? Well, this is where gradient flow works. Again, there is a phase here where gradient flow, at long time, it's stuck in spurious minima. By the way, it works a bit less good as Langevin. Langevin would work until here. Okay, that's interesting. If you want to know the formula of this line, this is it. Okay, so this line is in perfect agreement with our simulation, so we understand everything. We are really happy. Now, one thing you may ask is, okay, why isn't gradient flow working? And the hypothesis is, well, probably because it's stuck in minima when they are minima. So can we actually compute the property of the landscape, compute how many minima they are in such models at a given value of the energy for delta 2 and delta 3 fixed? Turns out we can do this. And this is done by applying the Katz-Rice formula. And actually for this problem, we can compute that kind of quantity, the logarithm of the expected number of minima, conditioned to be at a distance at the overlap m, and having an energy with respect to the matrix epsilon 2 and with the tensor epsilon p. Okay, we can compute these. In fact, it's a generalization of computation that was done by Gérard, Songmei, Andrea Montanari, and Nika a few years ago. So we really did it, including the spike. Okay, it's essentially putting the spike on this. So we know how many minima there are. Okay, and if you worry that this is an annealed approximation, you should not, because we also did it with replica and we checked that annealed is equal to quench, which is not easy to prove, but yeah, we didn't prove it. But okay, we all trust replica. And so what happens is that indeed we found an exponential number of minima. And so the kind of naive view that we have is that, since I'm in Switzerland, I think about someone going downslope on the ski lift, and you will get stuck when they have the highest number of saddles, because they are the most probable to get stuck. Okay, and maybe, and that's the kind of reasoning that was used on a very similar model by our friend in New York. Now, if you increase SNR, so for instance, delta 2 is fixed and you increase delta 3, or if you fix delta 3 and you decay delta 2, so having a better SNR, you may expect that at some point, there is less noise, things are less bumpy, and you get a trivial landscape with only one minima, the blue one, which has a positive overlap. Okay, and indeed, this is what you find. If you look at the computation, if the SNR is large enough, you have only one minima, or two if you have odd even tensor. And we can compute exactly when this is going on, when all the spurious minima disappear. Okay, so let's look when the spurious minima disappear. They disappear here. So that means that here in between the red line and the black line, gradient flow is still, still working perfectly fine, even though we still have exponentially many minima. Right? So that's interesting. That means that analysis in terms of just counting the minima is completely, naive, and it's not what is going to happen. That's not what matters. So,
Florent?
Before.
Florent?
Yes.
Hi. Sorry,
yes.
I'm trying to understand. So here, just to make sure that I understand correctly, the problem is harder when the SNR is higher. Right? This is kind of the opposite of the. Just making sure that I understand the direction correctly, right? Because the
SNR. Let's fix lambda p, okay?
So lambda p, when lambda p is small, that's you have a more. So when lambda p is large, you have more signal, and then you're on the left, and then the problem is hard.
Yes.
Right. So the problem is actually hard.
Yes.
So the problem is easy when SNR is small, and becomes harder when SNR increases.
Yes, but the problem. Okay. Yes. Also, you need to think that the problem is how much I can find. But yes, there are some interesting effects like this.
So how does that agree with the caricature you had before? Because I mean, usually we think the caricature is the SNR increases and then the local minima go away, but here the SNR increases and the local minima appear, right?
We can have a long discussion about this. Can we fix delta p and just be on this line?
Oh, so now you're going up and down on that. Okay, then the SNR goes the right way, right? I see. So you're going vertically, and I'm thinking horizontally. Okay.
Yeah. So think vertically. Okay. But good point.
Okay.
And I don't want to answer this now; it's too short. Okay. So think vertically, and now you may wonder why it is that there is a scission with exponentially many minima, and yet it works. Okay. And so. Actually, there is a perfectly reasonable explanation, and this is where I want to go. When you increase the SNR, okay, these minima disappear, but these spurious minima disappear, but there's not, it's not that magically they go away. In fact, they stay extremal point of the free energy. What happens is they are not minima anymore, and they start to develop, they start to have negative directions and becoming not minima, but shadows. So the question is, what you have to worry about is increasing the SNR, is what becomes of these minima as you increase the SNR. And now I have a bad joke, sorry. What you have to worry is about the fate of the spurious minima. And I really apologize for the joke. And if you look, because you can do this, and if you look again to cat's eyes with a bit more care, you see that literally what is going on is that these minima start to develop when you increase the SNR, the negative direction precisely in the direction of M star. Okay? So what's going on is that instead of being stuck there, they actually help you to go in the right direction. And again, if you allow me to be cartoonish, you ski there and you avoid everyone else and you go to the minimum. And if you compute now another line, which is the exact moment where the top minima start to develop as negative direction, you have another line, and this one is the correct one. Okay? The moment where the highest minima develop a negative direction corresponds exactly to the moment where gradient flow works. So this is literal, we can see that this is what is going on. And okay, I think this is interesting because it's one mechanism where we can understand why you don't get stuck in this thing, and I will skip this, otherwise Lenka will complain. And I think I'm done. Okay, so I presented this spiked matrix model. I think it's interesting because we can compute many things. And we have these two interesting observations. MCMC is not as good as Langevin. Sorry, Langevin not as good as AMP. That's what I meant. And we have this model where we can see that minimizing is okay, even though you have exponential minima. It doesn't matter. And I think this is interesting. And there are many things that we can do. You will hear more about Monte Carlo in different topics later on. You can ask the same kind of question in other problems. I think Antoine is going to discuss phase retrieval. You can ask what about more complicated signal and the effect of prior information, and Bruno is going to discuss this. Or you may want to go into neural network and more complex problem, and maybe different kind of optimization algorithm. And there is a line of work by Lenka in this direction. So now we really stop. Just flashing the papers that correspond to this talk. And I'm happy to take questions. I don't know if we have time, probably not.
Let's applaud. If there are immediate questions while Bruno is setting up, because that will take maybe a minute.
No, it won't.
Okay.
We have some questions on this side.
Okay, Florent, in your, I'm still confused about the answer to Nazi's question. So in your phase diagram, suppose that I insist on going horizontally, right? Like,
yes.
Then it does seem like something super strange is happening, right? Because I can always just ignore the tensor and
You're right.
Use the matrix. So
let me tell you what is, okay, I'm totally cheating you guys, because the best algorithm is the following: ignore the tensor, then just look at the matrix. Take the leading eigenvalue of the noisy matrix and initialize your algorithm there. And then you are basically as good as AMP.
Yeah. Well, okay, but the initialization, the only benefit of the initialization is that it slightly increases your correlation with plant. Like, sorry, initialization, yeah. No, the benefit of the initialization is getting you to anything decent. And then if you run your algorithm a little bit after the initialization, you like slightly increase your correlation with the planted guy.
If you start by, all these things which are happening, which are funny, is that if you start randomly, well, you don't seem to, algorithm doesn't seem to realize that there is this information. And indeed, if you start randomly, it looks, it's actually true. It's better to have an algorithm.
That's if you start randomly on the landscape that you have insisted on by taking the matrix and tensor information all together and packaging it up into this free energy landscape, or not free energy landscape, into the the like likelihood landscape. Okay. So calling it a hard region is like, it's hard for a particular algorithm, but it's not like it's hard for polynomial time in that region.
Actually, AMP is perfectly fine. And as just told you, if you initialize with the spectral initialization, you're all fine. Now, the bottom region is hard for all algorithms I know. Well,
you don't even need to initialize the spectral. All you need to do is ignore the tensor, right? If I just run from a random initialization and I just run in the metrics, right? So it seems that what's going on here.
But if you include the tensor afterward, you strengthen the information and you have even better overlap.
Yes, but in terms of the transition of like recovery or non-recovery, you're fine, right? So kind of what's going on here, if I understand correctly, there's just two problems that give you information about the same thing, and one of them is hard, it's computationally hard, and you're just hurting yourself by paying attention to it.
That's correct.
You're hurting yourself in the initial search. You're hurting yourself in the initial search phase, but then there's some potential. If you could get close-ish, then you could use that information a little bit for some cleanup.
Perhaps we don't see that in these notes, but perhaps.
Yeah.
So to be perfectly clear, all this is true. My difficulty is completely artificial. However, the advantage is that with this model I can compute everything, which is good.
Why is AMP able to ignore the tensor?
Because AMP at the first steps, what is actually doing is, the matrix part is actually acting like a spectral algorithm.
And these better AMPs from like Alex and so on, would they also be able to do this, or would they get stuck in the tensor?
Oh, well, that you have to ask Alex. I think they would work, but you know, I don't think they, you know, analyzing AMP is super hard. They analyze the spectral version of AMP.
But even
But
that, because
sure,
that should see the
I'm pretty sure it would work.
I know, Alex, can you hear my question or no?
Yeah, I think if you run Kikuchi, it would work fine, the same as AMP, I would imagine, yeah.
Yeah. I mean, you know, as I told you, there is no real computational difficulty here. It's just a toy model where we can actually look what would happen if I, you know, just run off-the-shelf algorithm. And they are not working so well. And it's interesting to know why.
Okay, we should stop at this. We can continue with this.
Sorry, Nati, next time.
That's okay.
So let's go to the second talk, which is by Bruno Lorero.